Quantum teleportation is a method where you can transmit a particular quantum state from one position to another position by the use of entanglement. I think a lot of you have heard of this scheme, and possibly a lot of you have probably also seen how to derive quantum teleportation. But what I want to do today is to actually give you a sense of why this actually works and the tricks that are used to make this work. So firstly, let's just recap. So when you have quantum teleportation, you first start with Alice having two qubits. One of them is an entangled pair shared with Bob on the other side. And what happens in quantum teleportation, firstly, is that you entangle the two qubits that Alice has. You perform a measurement. And then at this point, Bob has a version of the state which is already a little bit similar to the state that is required to be teleported. Then Alice calls up Bob, gives some classical information. Then Bob does a particular unitary process to convert the state into the desired state. So the quantum circuit for it looks something like this. And you can go through the maths and surely it will give you the state on Bob's side. But what is the secret of how this actually works? So actually what it really relies upon is this idea of a rotational invariance of a spin singlet. So let me explain what that means. So if you have the total spin of, say, 2 qubits, then the total spin operator is written like this. You can write the Hamiltonian for this system in this way, where it's the total spin squared. So many of you have probably seen this in terms of this is a Heisenberg antiferromagnet, and it's an antiferromagnet because there's a plus sign in front of the total squared. So the energy levels, we learnt this in condensed matter physics. The lowest energy state is this singlet state, and there's 3 excited states. These are the triplet states, and they have spin total 1, whereas the singlet state has a total spin 0. So this singlet state is actually where the magic of this whole teleportation kind of comes from. The singlet state is a unique state where you can actually perform a basis rotation and it actually looks exactly the same in any basis. So for example, here we have written the 0 and 1 states in terms of the plus and minus states. So what I want to emphasize here is that this is actually exactly the same state. So you start with the singlet state in the 0-1 basis, and you can rewrite this exact same state in terms of the plus-minus basis because that's just a different way to represent it. And as you can see that the state is actually still of a singlet form. So despite having written this state in different bases, normally this state would look entirely different if you write it in a different basis. But in this plus-minus basis, it still looks like a singlet. And in fact, you can do this for any type of basis where you start with 0-1, rewrite it in an arbitrary basis. Here, the theta phi here is an arbitrary basis. And it still looks like a singlet. So this is really the magic of the singlet state. And this is what you take advantage of when you do quantum teleportation. So let's do a simplified version of teleportation where there's only 2 qubits. So let's start with this singlet state. And then what Alice can firstly do is to perform a measurement, and she's going to measure in this theta phi basis. Then what she'll get, because there's 2 states in the superposition, there'll be 2 outcomes, each with probability half. First one, Alice will get the theta phi, and Bob will get the state which is orthogonal to that state, which I'm calling theta phi bar. The other outcome of Alice is the reverse of this. So she gets theta phi bar, and then Bob gets theta phi. So what Alice can do then is Alice can phone up Bob, and then in order to make sure that Bob has the right state, she can tell Bob what outcome she got in her measurement. So in the first case, when Alice gets the theta phi state, that means Bob's got the theta phi bar state. So it means that Bob needs to do some kind of correction in order that Bob gets the state theta phi for both cases. So there's something you can notice here just by looking at these states, which is that actually there's no transformation that you can do in order to turn theta phi into theta phi bar, or vice versa in this case. So, for example, let's say we applied a z-gate to the theta phi bar state, where our aim is to try and turn this state into the theta phi state on the bottom. So what you'll get here is we've got the right sign now, so we need a mutual plus sign. But then if you apply another x-gate, what's going to happen is that we're going to have this phase of e to the minus I phi instead of e to the plus I phi that we were supposed to get. So we have the wrong phase between these states. So you can see that there's no operation that you can do to make these states exactly the same. So this is actually what's called remote state preparation. And because there's actually no state or no operation that you can do to make these two states the same, you can instead just make the assumption that theta is equal to pi over 2. And if you make that assumption, then it's actually possible to turn these two states into the same state. So all you have to do is just apply a z-gate, and these two states become the same. So taking this idea from remote state preparation, this is what we can do to fix up that problem that we were having where we couldn't transmit to Bob exactly the right state we wanted. So instead of starting with 2 qubits, this time we start with 3 qubits. And the first thing that we do is to entangle this qubit that we want to transmit to Bob with the entangled pair. And then we can perform a measurement on the first qubit that Alice has. So what this will do is to transmit to the second qubit a kind of version of the state with the same problems that we had with remote state preparation. But if we do it again, then it fixes the problem because 2 of these flips that we were having is actually cancelled out, and eventually we can actually transmit the state that we wanted up to some kind of unitary operation. So then after that, all Bob has to do is to perform the corresponding unitary based on the classical information that Alice sent. So this is basically the secret, I think, of teleportation. It really relies upon this idea of rotational invariance of the singlet state. And really, when you do the full teleportation scheme, you can see this because when you perform the circuit at the point just before the measurement, you can see that already at Bob's end, you have basically the right state that Alice had up to some kind of unitary rotation that Bob has to do. So I hope this video was helpful in terms of getting a little bit more insight into quantum teleportation. If you want to learn more about quantum teleportation, then I have some other lectures on it. The links will be in the description.